In capital allocation reviews that precede major operational efficiency initiatives, finance and operations leaders often examine AI automation proposals that project full cost recovery within 18 to 24 months under standard volume assumptions. The model looks familiar. Upfront investment appears contained. Variable expense declines over time. A clean crossover point shows when cumulative savings exceed cumulative cost. The decision aligns with established efficiency logic. Yet once the system enters sustained operations, that recovery point often moves. The question is not whether the automation creates savings. It often does. The question is why the payback horizon that appeared precise at approval becomes longer and more sensitive once the system operates under real conditions. The common economic illusion is treating AI automation as a discrete investment whose costs amortize cleanly through direct substitution. In practice, the commitment is not discrete. It includes model preparation, data pipelines, workflow embedding, infrastructure capacity, validation routines, and ongoing operational support. What appears contained in the approval model becomes a layered cost structure that resists contraction. The recovery horizon does not extend because the automation fails. It extends because the cost structure changes shape after approval. To clarify the relationship, consider a simple economic schematic. Two lines traced over time. One represents cumulative capital outlays, rising sharply in early periods as development, infrastructure, and integration costs accumulate. The other represents cumulative savings, rising more gradually as variable expense begins to decline in operation. The crossover point is the true recovery horizon. It is not the moment of deployment. It is the moment when accumulated savings finally exceed the full burden required to build and sustain the system. This relationship is simple, but it reveals the central constraint. Recovery depends less on the headline saving per task and more on how long those savings must persist before they close the initial gap. Across these dynamics, the pattern is consistent. Fixed cost expands, variable cost compresses, and recovery depends on how long that gap remains open. Automation often converts costs that were once variable into a structure dominated by fixed commitments. Manual effort declines, but compute capacity, integration overhead, data maintenance, validation processes, and specialized support become embedded in the system. The cost appears lower only under narrow utilization assumptions. If volume is high and stable, fixed costs can be distributed across activity, and marginal cost compression becomes economically meaningful. If utilization falls below expected levels, the fixed burden remains, while savings accumulate more slowly. The economics hold only while utilization remains aligned with the original assumptions. Early models often assume smooth absorption into operations. They assume workflows adapt quickly, demand remains stable, and support requirements taper after launch. In practice, integration does not resolve at go-live. Data flows require adjustment, outputs require verification, exceptions require handling. These costs persist as ongoing operational requirements rather than one-time expenses. The gain is real, but only if integration burden remains contained. Maintenance introduces further pressure on the recovery timeline. Model performance shifts as inputs change. Business conditions evolve. Each retraining cycle, data refresh, or validation pass behaves less like a small variable cost and more like a recurring capital commitment. What appears efficient in the approval model can quietly relocate cost into later periods. The compression point emerges when the full cost structure is visible. The system reduces certain operating expenses in the visible layer, but it adds infrastructure, oversight, refresh burden, and integration overhead within the same system. The advantage is real, but narrower than the headline timeline implies. The recovery horizon is therefore governed by three operating conditions. Utilization must remain sufficiently high, maintenance cycles must remain sufficiently contained, and system complexity must not expand faster than the savings it generates. The apparent efficiency depends on conditions rarely sustained at scale. Even after the initial crossover point is reached, cost stickiness remains. Infrastructure commitments, vendor dependencies, embedded workflows, and specialized support do not contract proportionally with demand. Capacity may be technically scalable, but economic commitments often persist. Costs that scale with activity in the model often persist even as activity declines. Organizations that track recovery in practice do not rely solely on the initial projection. They stress test the crossover point against lower utilization, slower adoption, higher exception rates, more frequent refresh cycles, and greater support burden. This reframes recovery from a single date into a bounded range. A stronger economic model treats cost recovery as a range, not a date, because utilization, maintenance cadence, and integration burden rarely stabilize at the same time. This distinction matters for capital allocation. A system can deliver long-term value while missing its initial payback window. The question is not whether recovery occurs exactly as forecasted, but whether the fixed cost base remains justified relative to the realized and sustained savings. The schematic relationship remains central. The crossover point shifts whenever upfront commitments expand, recurring burdens increase, utilization weakens, or savings arrive more slowly than expected. In practice, recovery is shaped by the interaction of utilization, maintenance cadence, integration friction, and cost stickiness across the operating system. As systems mature, recovery timelines stabilize only when utilization remains consistently high and complexity growth remains controlled. When volume declines or maintenance burden increases, fixed commitments reassert themselves and the horizon extends. The capital reality operates within these constraints. The underlying physics of cost structures shapes outcomes more than the technology itself.